All right, what's up, everyone? Welcome back to some structure-free learning. And, today we're going to go back to some mechanics of materials. And in this video, we'll do something that a lot of people have requested and talked about, and that's transverse shear, or just transverse loading on beams and the internal shear that it causes, and how that internal shear ends up in stress or shear stress. So hopefully by now you have been looking at axially loaded members and beams. And if I were to take a simply supported beam here with some sort of, let's just put a distributed loading on it like this here, you're able to calculate reactions. You make a cut over here, and on the inside of that cut you would note that here on the inside of this cut there is an internal shear that, let's see, pi, it would be in theory positive downwards, and then a moment here, bam, bam, and V. And so you know how to calculate the stress due to moment, and the stress due to this moment is a normal stress. Sigma is equal to minus my over I, right here. So hopefully you've covered this. This is the normal stress due to moment or bending. And then here, we want to figure out what is the stress or the shear stress, obviously, from the shear force. Shear stress due to shear force. And shear force. And we're going to use the symbol tau. And the equation that you maybe have seen is T is equal to VQ over IT here. And I'm going to show you where this comes from. So hopefully in this video I can explain to you where the transverse shear formula comes from, and then apply it for a very simple example problem, and then show that the distribution of the shear stress is actually parabolic, as opposed to here, which is, the normal stress due to bending is linear, but the shear stress due to the internal shear force is parabolic. And I don't know if I can do this all in 10 minutes, but we'll just break this up into parts, and probably this will probably take 2 or 3 parts. So let's enjoy as we go. And the first things first, let's talk about beams. Okay, so let's consider the following beam. Consider this right here. And let me say that I have a beam here. And let's say it's unmodded. So I just take a bunch of boards or pieces of wood right here like this. And I lay them flat on top of each other without putting any glue or nails or anything to the board here. Okay, right here. And let's say I just, put it on some sort of supports here, I attach it, and I apply a load to this right here. Now, when I look at the deformation, if it's unbonded right here, if I zoom in right here, man, look at that, my zoom in arrow. What's up, right? Anyway, in right here, what I would see on this edge with the deformation in an unbonded, so this would be unbonded beam, is like this. I would see this jagged edge. Let me make sure. Hopefully I didn't. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5 right here. And this is what it would look like in terms of my deflected shape right here. When I deflects right here, I see all these I see this jagged edge. It's not continuous. Uh, all of our beam equations really just fall apart because of this, but it's unbonded. And so what happens is, because it's unbonded, they're not able to transfer any forces between the layers, okay, or stresses between the layers of the boards or the material. And so this is not beam behavior. In fact, you can't even use sigma equals my over I, because here you do not have a continuous edge here. This edge is not continuous. It's jagged. So even sigma equals my over I, and the strain profile is no longer linear there. It's all jagged and a bunch of discontinuity. So this isn't even a beam. In order for you to have beam behavior, you actually have to have these layers bonded. And if you do bond those layers, so here, this would be my bonded drawing. Bam, my bonded drawing over here. If it's bonded, all my layers are bonded, then what I have is, I would see on the edge, it would look nice and smooth here, and I would see, bam, like this, 1, 2, 3, 4, 5, a nice continuous slope. And so this is how it would look like on the bend. There would be a rotation of this edge, and this edge would be smooth because I can transfer in between these layers. I can transfer shears. I can transfer shears, and and it keeps things together. And you can, you can try this with a stack of paper, and if you bend a stack of paper, you can see the edge. If you zoom in close to the edge, you'll see the jagged edges. And so what you have here is you need these layers to be bonded, and in order for you to have, satisfy beam theory here, and this having being a continuous strain or continuous deformation here, smooth, not jagged, okay? And this is even more important when you do like composite materials and things. But so here, so that's what we have. Our beams that we're going to use in mechanics and materials are this thing right here. Okay, we assume that it's bonded to layers, and we that means that we assume that shear stresses can be transferred between layers. Okay, and that the beam is capable of resisting shear. All right, so let's find out. Let's look a little bit more now at what it means or where this shear stress formula comes from. So if I consider now just let's just take a regular beam here. So here's my beam. Bam, that's pretty good. And we'll make it simply supported. Keep it simple for now, right? And let's say I have some distributed load that's all crazy, that functions or varies with x right here. Okay, it's all changing and stuff right here, and it has some length and all this stuff for it. And even the cross section looks a little funky. Let's say it has this, and that this is my centroid, my geometric centroid over here. Okay, my geometric centroid. So this is my cross section view right there. And if I take this section and I make a cut here, say I make a cut, and I make a cut here, and I say it dx, and I isolate this segment. So I want to zoom in on this segment right here, and I want to, bam, I zoom in on this one like this right here. And if I look at that segment right here, so here, let's see, let me draw this segment. Boom, boom, here's the segment right here. This has a width dx, okay? And let's say my moment is changing, right? So I on the one side of this right here, I have my positive moment here, and then on the other side, some m plus dm, some incremental change. That incremental change could be positive or negative, right? But anyways, it's some incremental change here. And in fact, if you remember, if you make a cut and you look at the right side of the cut, which is this right here, you would say that the shear goes upwards over here, and on the left side of the cut you would say the shear force goes downwards over here. Okay, and it would be like v plus dv, like v plus dv or something like that. All right, but that's not so important. If I draw, so let me erase that. I don't need that right now because I want to draw the normal stress profile here, this normal stress profile here. So if I have my neutral axis is right here, so this line, let's say, represents my neutral axis. Let me make it a little bit higher up. So let's say this line over here is my neutral axis. So the normal stress due to moment looks like this. On this side, I have some stress, let's say here, and it will, some normal stress here, which I'll call sigma, and I'll just bam, bam. And this is really a volume, but here I'm just going to draw in 2D, and then here I have another stress. They should not be the same magnitudes, right? But here I have another stress there. And then over here I have incrementally, if it's increasing, I'll just draw a little bit bigger, assuming that it's increasing. This would be some other stress, sigma prime, and then some even, whoa, I got to put one side in tension. So let's say the top is in compression, and the bottom is in tension, like this. And then same thing here, in tension, okay? And this side, the top half is in compression here, or the top, anything above the neutral axis is in compression. And here is my neutral axis, which also represents y equals 0, right here, okay? And plus y would be defined this way, okay, right there. And here, if I look at this, and in particular, if I make a cut somewhere, let's say I make a cut right here, okay? I make a cut and I look at the top half. So I make some cut at some distance y1 right here, okay? I make a cut and I look at a free body diagram of that cut. So let's go down. Let's go right here. So if I look right here, I zoom in on the free body diagram of that cut, and here's my blue cut line right here, and my stress, my sigma prime, might look like this, trapezoidal, but again, still a volume, right? And here's my other side, sigma, which might look like this right here. And what I have to ensure is that even though these sides are unequal, I have to have equilibrium. So you would suspect that there is something else happening here, which happens to be the shear between layers, right? This tau. And and here, if I have to enforce equilibrium, and let's say that if you could see a 3D view of this thing right here, this side right here, I don't know how I would do a 3D view, but this side right here, this area right here, this area, this line right here, which really represents in 3D an area, surface area. This is this dA above the cut. And I'll call that dA prime or dA1. Let's use dA1 right here. dA1 right there, okay? And same thing here. This is also dA1 too, right? It's the same area, and especially if dx is going to be small, right? And so here, I have to enforce equilibrium. So many derivations just come from equilibrium. So here, from this cut segment, I have some of the forces in the horizontal is equal to 0. What that tells me is that the force of the stress block here, this sigma, is an integral sigma times dA1, okay, plus this right here, plus, let's do minus right here, sigma prime dA1, okay, plus tau, which is the shear stress right there, times the area that shear stress is acting on, which is really the dx times the thickness or the width of my material here times, I'm going to use B, okay, for the width of the material, B here, equals to 0. And the idea is that the surface here, if I were to look at it in 3D, or at this location right here, if I could look at it in 3D right here, I'm going to try to draw a 3D surface. It would look, something like this, okay? Can you see that? And this right here, this distance represents dx, and this distance right here, this width at y1 represents b, okay? The width at the location I'm interested in, if you will, right here, this b. And then all this right here, or these little increments, if I add up right here, this represents dA1, okay? And so here, I've got this equation now here. And so what you would do now is substitute for these normal stresses. And this normal stress here, just from mechanics of materials and just what you learned from before, this is on the left side here. And the calculation for that is m times y over I times dA1 right here, minus m plus dm over I times dA1 plus tau dx times b equal to 0, okay? And if you look here, this term right here is essentially, if I multiply through dA1 and I, is this term right here. And so I can say in red, this cancels with this value here. And what I'm left with is that tau times dx, tau, let's do this, tau times dx times b is equal to dm over I times y. I almost forgot the y here. Okay? Almost forgot the y in the normal stress calculation. dm times y times dA1. Bam. Okay? And what this says even further is that here, if I is constant, tau is dm over dx times 1 over IB y dA1 right here. And this right here, if you remember from the shear moment diagrams, we said that V is equal to dm dx, or the slope of the moment diagram is equal to the value of the shear. And so this tau is V over IB times y times dA1. And this term right here is what's called, this area times y. It's a first moment of area. First moment of area. And in particular, it's the area, the moment of the area about the neutral axis, about area, really is like dA1, right? Or A1, about the neutral axis, about the NA right here, about the neutral axis. So that, and sometimes they use that symbol Q. So they'll use the Q symbol here, capital Q. And so what you'll see a lot is that this formula here, this tau, is equal to VQ over IB, or in some other textbooks, it'd be VQ over IT. Okay, and this is it, and that's the derivation for the shear stress formula. Okay, hopefully that was enlightening. That was a little bit longer than I thought, but come back.